Good morning. So I know a lot of you here are here to learn about about new tools. Um, well, I'll speak up. Okay. So I know you're here to learn about new tools in this field. I'm gonna talk a little bit in a more general way about mobile biometrics, the development of mobile biometrics, and how that might inform the development of remote intelligence systems. Okay.
Could you also just give us some rough idea what the company does?
Sure. Okay. So my name's Terry Riopka. I'm the director of research at Aware. So Aware is a biometrics company. So we've been in the area for about 30 years, actually. And we've developed various software. All our code is developed in-house. We've developed code for face recognition, for fingerprints, for iris, we've used behavioral biometrics, and most recently voice. And we've also done work in text analytics as well for entity resolution. So we've done a variety of different types of work. We've got a lot of in-house IP, and we're trying to extend that into various commercial areas. So this is just an overview of what I'm going to talk about today. So I'll talk a little bit about what we use biometrics for. I'll talk about some of the enabling technologies for remote intelligent computing in general, and then I'll present biometrics as sort of a case study. It touches on edge versus cloud computing, so I'll discuss that, and then I'll talk a little bit about what it's like developing under the constraints of mobile and the mobile environment. Okay, it's still not switching. It's still not switching slides.
I think your mouse is on the wrong screen. That's why it's not. So if we go in the PowerPoint, click on the screen, and then we.
Okay. So we've seen biometrics start being used in a lot of different areas. We've seen it being used for controlling access, attributing accountability in law enforcement and defense, and then personalizing services. We've been able to create very secure mobile ecosystems which are driving commerce by lowering the friction of user interactions and simplifying financial interactions. Mobile biometrics also spurred the expansion of on-demand infrastructure and the proliferation of sensors that are being used by these devices out in the field. So the reason there's been success in a lot of these areas is because there's been this sort of confluence of multiple factors. We've had increases in the power of computing hardware, both in the size of the hardware that's being used and the power of its computing capabilities. We've got ever increasing power available to us for computation. There's a lot of sensors being used by devices out in the field. They're cheap, low power, a lot of different sensing capability out there, and we also have obviously Wi-Fi and high bandwidth connectivity that allows a lot of data to be transferred. And then, of course, we've got the improvements in machine learning. The latest advancements in machine learning have drastically improved the capabilities of the algorithms that we can implement. And of course, none of that could be happening without the large scale availability of the data that's out there. So, of course, that's been the consequence of the sensors that are available out there, the sensors that are getting the data from the external world, and then, of course, the high bandwidth that's enabling that data to be streaming into computers that store that data and analyze that data and can manipulate it. And of course, I'll mention, this isn't related to biometrics, but of course you've heard about the Internet of Things. This is going to spur even more development in the area. As you're able to communicate with more and more devices, put hardware on smaller and smaller devices, and have all of that interact with the cloud. So let's talk about biometrics. So I just want to give you some idea of what's involved in mobile biometrics, some of the capabilities that we have to implement, how we implement them, how we divide those resources between the device and the cloud. So taking one application, think about enrollment or authentication, or where you're trying to authenticate your identity. So there's a lot of factors involved in developing mobile apps for this. So it's not as simple as just matching a biometric. So you're not just taking a face and trying to find a face. There's a lot of supporting infrastructure that's necessary for developing applications like this. So one of the functionalities you need is, for example, auto capture. So you have to have on-device image acquisition, and you also need to have some sort of quality assessment in real time. So you need some sort of feedback to the user that's using the device. This all has to be user friendly, has to be fast and actionable. You want to provide information that's useful to the user, and this is all in order to get to create this low friction process. Because face it, if something takes longer than a few seconds, people start getting people upset and antsy, and so to enable this kind of technology to proliferate, you need to address these kinds of issues. Yeah.
When you're talking about low friction, what's the difference between user-friendly, fast, and low friction? Isn't user-friendly and fast the only things that low friction consists of?
Well, I guess you could. That might be a little redundant, but fast and actionable feedback I mentioned specifically because that's related to the information that you're getting from the device. Okay, so if you're talking about interacting with the cloud, there's going to be issues with that, right? So you don't want the latency associated with cloud communication in order to provide feedback for, say, quality.
That's included in fast, right? What low friction means besides user-friendly and fast?
Yeah, well, like I said, it's a little redundant, but low friction, obviously you want the entire transaction to be low friction, right? So you want a very smooth transaction, you want minimal required interaction between the user and the device. So yeah, you can think of these terms as somewhat redundant, but I'm just trying to make that point. Sorry?
It has to work.
Right. I mean, that's right. So there's different aspects to that, right? So it does have to work, right? Okay. So what else do you need? Well, in the case of authentication, you need some sort of liveness capability. So you need to be able to prove that the person who's using the actual device is the live person. And so how do we do that? Well, we have to. It takes a little bit more sophistication to compute liveness. In our case, we transfer image data from the phone to the cloud. We do some processing on the cloud, which then sort of looks at the biometric, tries to determine whether it's some sort of spoof potentially, and then it returns a response back to the user. And in a case where you might reject the user if you determine that the person is trying to spoof the system. So again, here you have this balance between what's happening on the device and what's happening in the cloud. And that's related to the amount of computation that's necessary to do the actual algorithms. And so In the case of auto capture, you have to do the stuff on the phone because you need that fast interaction with the user. In the case of liveness, there's more sophistication to the algorithms. They might take a little longer, and in our case, we've decided that we're going to be implementing that on the cloud. And then, of course, after this, you have any kind of multi-factor analysis that you do to actually match the biometric. And so this may include image data, or may include some sort of sensor data, or combination, or even multiple biometrics. So in some cases, we use face and voice, depending on the scenario, the type of security that you want for the system.
Like for example, this map you have for
Yep.
the face, how much bandwidth are we talking about? What goes to the cloud?
Right. So in our case, and that's definitely a factor. And I'll discuss that a little bit in later slides. But generally, in our case, we're talking a stream of images, and of course we take some efforts to compress that data to minimize the size of that.
So like would a 24 odd GDG, right? What about 5060, or I need to have at least a 2G?
Well, I'll talk a little bit about that because that is a factor. And we've tried to move to different markets. So depending on the market that you move to, you do have to take into account that those kinds of issues. So we have made efforts to reduce the amount of bandwidth necessary to implement this. In the case of Africa, for example, we've done a lot of business there, and in their case, the cost for sending data is significant, and so they want to minimize the transaction costs associated with that. And so, yeah. But in our case, we're talking a stream of images anywhere between 2 and 5. You know, two and 5, sometimes 10 images, depending on what we're doing. So, and of course, in the back end, you also have the possibility of having distributed processing for, let's say, large matching applications. So if you're matching, let's say you're talking about a fingerprint application for law enforcement, they might be matching a very large database of individuals, in which case they might do some back end distributed processing to enable that to happen quickly. Yeah?
So if your data gets stolen, you just replace the password. If your biometrics get stolen, what are you going to replace the face?
Right. Right. Well, that's a very good question. So there are a lot of different approaches to solving that problem. So one of them obviously is encryption. So to limit the ability for a hacker to take your data. Another one is for we've been working on recently, referred to as biometric tokens, and that's where it's sort of it's a cryptographic biometric method that's essentially obfuscates completely the biometric itself. So you could steal the face token and be unable to actually reproduce the biometric behind it. Yeah.
As you all know, anything on a blockchain is cryptographically encrypted, and yet there's been plenty of hacks there.
Right.
But that's just your money. If your retina gets stolen, you're not going to replace an eye.
Right, but that's why there are these liveness detection algorithms, for example, right? So that's, in some ways, it addresses that to some degree, because if a person does steal let's face it, your face is available on the internet somewhere, right?
I'm not talking about face, I'm talking about retina or fingerprint.
Right. Well, in that case too, in order to use that data, they have to actually, in the case of fingerprint, for example, they have to actually create a dummy fingerprint in order to use that data to access your biometrics on some other system, right? So again, it's an instance or example where spoof detection is actually needed and useful. But that's an excellent question. Like I said, there are other approaches that we're taking to try to eliminate the possibility of even being able to reproduce a biometric.
Are you able to talk about them?
Not the details of it, but just the fact that we're working on it.
But not that's all you could say. You couldn't say what kind of
I mean, they're not as accurate. I mean, to be clear, I mean, they're not as accurate as actually using the biometric, because you give up some of that ability in order to obfuscate the information. But I can talk a little bit more offline if you're interested.
Response.
Well, no, I mean, we've decided not to, simply because it adds friction to the whole system. So we've been extremely successful in the liveness algorithms that we've developed. They are capable of detecting liveness of using actually individual images even. And they can tell the difference between, pictures and videos and 3D masks and all sorts of things. So they've been very powerful, and so we just haven't found the need for it. We've tried to avoid it, actually. And the other reason is because it's also they're less accurate, right? So they're less secure. So a spoofer who would, let's say you had a multi-factor ability, right, where you do both, they're always going to go the path of least resistance, right? He's going to know that the algorithms are more accurate, so he's going to fail on the algorithms, and then he's going to fall into the second tier of using the challenge response, and then try to foil it that way. So spoofers always go to the path of least resistance. Well, replay attacks, again, well, that's a more complicated one. You have what's called injection attacks, for example, right? Well, actually, you're talking replay attack is pretty easy because you're detecting display devices. So but when you're talking about injection attacks, that's where you actually take a stream of data and funnel it into it, circumventing the acquisition device. Then you're talking about more difficulty. Right. The way we handle it is we have what's called, again, this is going into a lot more detail, but we have what's called the bright screen algorithm, and that actually, sorry, it's called the bright screen algorithm, and what it does is it actually it flashes the user, right? So you actually have a flash imprint on the user, and so you're creating that connection between the transaction, the real-time transaction, and that's something actually physical on the 3D scene, right? And that connection connects the transaction and prevents injection attacks, because you have to have that in order for you to be clear that the event that you've captured is a real-time event on the device. So there's a lot of aspects to that are very interesting. Okay, so let me continue here. Okay, so, and of course, surrounding all of this, you have to secure these transactions. So you have to have encryption in a lot of different areas of the system. Okay, so this thought about, when you see these terms, edge versus cloud computing, it makes it sound like it's an either or, right? So in the case of biometrics, it's definitely not that, okay? It needs to be some combination of the two. And so how do you decide about that combination? Well, you have a lot of system issues that you need to deal with in a biometric system. So one, obviously, you're concerned with accuracy of the algorithms. You're interested in response time. And so you have the system response time for the entire transaction, but then and then you have algorithms. Oops, sorry. Let me go back. So you have the algorithm security, and again, security here in this case is there's always this tension between security and convenience, right? So the more convenient you want the algorithm, the less secure it typically is. And the more secure it is, the less convenient it is. And your accuracy determines the overall relationship between those two. So that's a very important set of factors. And then you have data privacy and security. Obviously, that's encrypting the data. And then is there a way to obfuscate it or prevent somebody, even if they get it, from using it? And that's what this lady asked about. And then you have, obviously, communication bandwidth, data limits, for the environment, right? So if you're deploying this in Africa, for example, there's more stringent limits on bandwidth that you have to consider in that marketplace versus if you're deploying in the US, let's say. Operational configurability. You want to be able to configure the system. You want to adjust thresholds, let's say, to adapt to different scenarios, and of course, cost, and that's always a big factor. So you have these system issues. There's different ways to get to the same point using edge and cloud. And how do you decide between the two? Well, you have computational resources. So you have certain limit on the device, certain limits on the cloud. In the case of mobile, you have a lot of different phones out there, right? And those phones could be pretty old. They could be as old as 10 or 15 years. So you have to think about the possibility of those phones implementing your algorithm. On-device application footprint is extremely important for some markets. You can put a lot of stuff, okay, so you know yourselves, some of the TensorFlow models, they can get very large. Putting that all on the phone, even though the phone can handle it, it may be an issue in some markets, right, where if a person needs to upload or update an application, they don't want to sit there for an hour downloading a 200 megabyte application, even though the phone can handle something like that. So those are issues, and those are mostly economic questions. And then you have, of course, response time you see here in all three areas, right? You have response time for the system, response time for edge for the phone, and for the cloud. It clearly depends on what you're doing, right? If you're doing real-time feedback, quality feedback, you have issues about response time on the phone. If you have liveness on the cloud, you have issues with response time there. And then, of course, the overall system response for the entire transaction. And then version update policy, again, that affects how often you download, the size of the package that you download. These are all relevant points. And on the cloud, some of the main ones that are slightly different are throughput. So if you have the cloud doing a lot of, let's say in this case, liveness computations, you have a lot of transactions coming in. So you have to be able to handle that. And so degree of parallelism that you include on that side, these are all issues that you need to deal with and in the final design. So you might think of this as sort of a tug of war between the two, and it's really better to think of it as a collaboration, right? Because ultimately you decide on the optimal uses of your resources based on the application or the scenario that you want to operate in. So let's talk about a little bit about the developing in this environment. You guys are going to be working on a lot of different applications, but as you start working on complex applications that require this interaction between mobile and cloud infrastructure, you need to consider some of these issues, right? So transaction logging is extremely important, okay? So this is basically documenting or being able to look at the data that's coming in, right? So for data monitoring purposes, right? You want to know during development and then even after development. So a lot of these tools make it to our customers, right? So we give a lot of these data monitoring tools to our customers so that they can monitor the progress, they can collect the data, they can analyze the operational statistics of the performance, and so they can provide us feedback, right? They can talk to us and tell us about how operationally the system is working. It's extremely valuable for us as developers to know how the systems are operating in the field. And then data collection for testing, training, post-deployment. That's extremely important. You want to be able to store that data, potentially using it for training or testing. And I say post-deployment because some of our customers that we collaborate with save this data and eventually come back to us and say, hey, if we give you some of this data, can you improve performance of the system? And the answer is often yes, and we do that. So what else do you want from a system that you're developing, right? So what you want is you want configurability for system parameters. You don't want to keep rebuilding all your apps all the time, right? When you're developing this complex system, you want to be able to also incorporate the ability to configure it for certain parameters, right? So you want to optimize the system over time, and you don't want to just you don't want to keep hassling software engineering to keep redoing builds all the time. You know, in larger environments, you know, software engineering is not just doing your project, right? They're doing a whole bunch of other things, right? So for you to get them to work on your stuff can be problematic sometimes, and so as and you have to remember, I'm talking from a research standpoint because, you know, I need to get to develop the algorithms and to implement. I need to interact with software engineering to get them to do a lot of the things that we need done. And then I talked about ground truthing. Machine learning is just becoming a part of the world, and so you're going to have this data coming in regularly, and you're going to want to use that. And in order to use it, you're going to need to ground truth it with consistent and expandable labeling. So you're going to need resources, either human resources or automated resources, to provide that ground truthing. And you probably want to do it on a regular basis because your data is coming in all the time, and you know, you can't just say all of a sudden, hey, tomorrow I need, you know, 1 million images ground truth. So you need to plan ahead, and you need to provide an environment in which you sort of maintain this sort of regular system. And of course, data storage, these are mundane things, but really they're important. You need to be able to properly name the data. You need to have it stored in proper places. You need to also maintain independent test sets. Okay, so we keep maintaining independent test sets as we progress with our development, so that we have sort of test sets from a long time ago that we've kept independent of everything else, and that's really just to monitor the progress of the algorithms. So that's extremely important, and it needs to be considered. Yeah.
As far as training data and labeling, do you have any benchmarks, or can you comment on like the ethics and implicit bias that might come with the machine learning and labeling stuff in AI, as far as like skin color, ethnicity, race, or any of that? Do you have any data on that, or do you have?
Yeah. So that's a very good question. So our company actually, we take a little bit of pride in the field to claim algorithms that actually try to address those issues, right? And I'll give you an example. In face recognition, for example, we don't do that well there's this sort of national FRBT test for, you know, we don't do particularly well on the main in comparison to a lot of the vendors. We're not horrible, but you know, but we're top tier in anti-bias. Right? The reason is because the specific algorithms that we implemented actually make use of classifications that are not race oriented, right? So they're more face structure oriented, right? So whether you're you have Asian background, or you have African background, or Caucasian, there's sort of common characteristics to faces that you can talk about without talking about race, right? You can talk about a large nose, for example. You can talk about certain features on the face, and in some way, and you can have sort of race agnostic features that are more general, that relate to the structure of the face, and that helps you design algorithms. And if you incorporate that into your actual algorithm design, you can mitigate those kinds of biases. The other thing is monitoring the bias, right? So if you have properly ground truth labeled data, you can monitor that bias by doing experiments, and we do that all the time. So we have empirical tests where we we try to identify what those biases are, and they could be they could be gender, they could be race, but we do make an effort to try to mitigate those biases.
So you're saying you can accurately separate facial structure, which can be so closely tied to like ethnicity,
Well,
and have be agnostic.
sorry, let's say that again.
Facial structure,
Yeah.
right? Like
Yeah.
people from different places look similar to each other, right? So like the structure can represent a particular subset of people. So you're saying that like it's agnostic to that, and there's no implicit bias in like the structure that might represent a certain subpopulation, for example.
Well, that's maybe an academic question, but the fact that we have been able to get top tier algorithms with minimal bias, even compared to very accurate algorithms, is, I think, relevant, right? It suggests that maybe there is something to that approach. Yeah.
Could you talk about the protocol for data storage?
Talk about critical data storage. What?
Protocol for data storage in cases where you're dealing with
Healthcare
healthcare data.
data. Well, we haven't really dealt with healthcare data per se.
It's not used in healthcare.
It's talking about like HIPAA and things like that.
Okay.
HIPAA is like the healthcare patient privacy.
Oh, yeah, we don't really have that much experience with that, so I can't really comment.
Do you know of any application where you use the biometrics and healthcare data?
No, you had mentioned that they are used in healthcare settings.
Well, I guess I was more generally just talking about applications, possible applications to healthcare, yeah. But no, we're not currently. We've done some authentication applications in healthcare. So where they're related to access control. So it's sort of tangentially related to healthcare.
So how does like this Okta or two factors? So how can you integrate this instead of having the push notification or into the code? Use your application like a biometric into Okta. Have you done something like that?
No, Okta? I'm not familiar with that.
Like, or you have like Google Authenticator, right?
Yeah.
So instead of using the two-factor code,
Yeah.
you use the biometric.
All right, so what's
Have you done that? So like, for example, just how many companies have the two-factor authentication, right?
right,
You log into a website
right,
and then they'll either get a push notification on your mobile phone,
right.
and then you either
You're asking if we've done that?
Yeah.
So we've collaborated with partners who implement that, right? So a lot of the technology we sort of provide a lot of the pieces that they put together in order to do that. So so I would say yes, but beyond that, I'm not sure what your question is.
No, I'm just asking.
Yeah.
So it's not part of the base product. It's like you're like the TensorFlow libraries and your partners are using TensorFlow libraries, right?
Well, we used to do mostly that, but now we've expanded to actually providing on-demand authentication services. So, in fact, a lot of the services that I'm talking about, we actually provide as microservices in a SaaS infrastructure. So, so we're moving in the direction of doing that. So we're
Are you like a snowflake like for biometrics in which I just say, aware I need this on demand
yeah.
and
Yeah.
take care of that. I don't need to set up my
Exactly. Exactly. So we set up all the services that you might require. So you decide, okay, do you want face and voice, or do you want face and some sort of push notification, or do you want whatever?
Then I have to set up my like in AWS language my own VPC, or it's more like a snowflake.
No, we handle all of that. Yeah.
You're turnkey.
Yeah.
I give you the first response, request, and you give me a response. Yes.
Yes, that's correct. Yeah.
Okay.
So we've got like 5 minutes more.
Okay.
So.
Yeah, we're coming to the close, I think. Okay, and then finally, one last point about the need for simulators. So you want to be able to analyze all aspects of your data processing pipeline offline. Okay, so you don't want to have to rely on the operational system. You also want to be able to reproduce operational data out in the field. So if a customer says, "Hey, this set of images came in and it's giving me the wrong answer," you want to be able to take that exact stream, put it on your local system, and be able to simulate the results. So that's extremely important. Okay, so for algorithm enhancement, so this is from a research standpoint. I talk about this. There's always this tension between the footprint on the device and improving performance. So that's constant tension for mobile development. And I have here is, I say you need to regulate the pace that you do the optimization. And this is really kind of a nuance, but it's important, right? Because as a researcher, the last thing you want to do is completely optimize your code on the mobile device from the very beginning, right? Get it as small as you can, as fast as you can. I mean, you think that that's like what you would want to do. But if you do that, then especially in the early stages of algorithm development, you get kind of tied to that, right? So the next time you say, hey, I've got a really great idea for an algorithm, but it's going to cost me a second longer on the device, that's a tough sell, because now all of a sudden things are going to get slower for the customer, right? And then you're in a spot, right? So the idea is not to. This isn't the tension. The hope is that you can plan this out a little bit, right? So you don't want to push too fast on the optimization side, because then you're really limiting on your algorithm improvement side. And that's a really important lesson that's hard to learn, because there's always pressure to do things as fast as you can, as small as you can on the device right away. And this is also, there's no substitute for being in the world. Okay, so being able to have your algorithms run in the world, in the operational scenario as fast as you possibly can, because that's where you learn the most, and that's where. Oh, that's great. Okay, I have to hurry anyway. So you want to minimize the impact on software engineering. It's important to have good, tight, iterative development cycle with them in order to enable that to happen. And then finally, it's good to have a good working relationship with your customers, because this lets you, they can supply you with data, they can supply you with feedback. It's very important, and it's something that needs to be needs to be done. Finally, I just want to add on end on a note, sort of a loftier note for you guys. I date myself a little bit here, because when I was a kid in the late 70s and early 80s, the future was the year 2000, okay? That was, for me, that was the future, right? So now it's been delayed a little bit, right? So it's been delayed, I think, maybe by about 30 years, something like that. But at least it's getting here, and I think it really is here, okay? So the future is here. You guys are going to be part of it. We're going to be developing applications, because of the hardware availability and the new algorithms that are out there, specifically the machine learning algorithms. There's going to be a lot of different motivators for this progress. And this is just a brief list of things. Stuff that's I call it low-hanging fruit, but there's a lot of the low-hanging fruit, okay? So this technology that we have now is going to last for a long time. I mean, when you think of, in terms of these AI winters, where you have sort of, hype, and then these AI winters, and then more hype. This hype's going to last for a little while, because there's a lot to do, and the algorithms are getting extremely powerful. And so there's going to be a lot of really fascinating application developments in the near future, and you're going to get this slow. We're going to have this slow migration of machine learning to the edge. Okay, it's going to happen, and when that happens, it's going to be really fun. So that's it. Any questions?